So in theory, this is where you started. Did anybody think that was pretty cool?
Yes.
Yeah. Just because I walked through this with my other class, okay? We compare these, okay? This is like saying 20 years from now predicting something about me, okay? The color of my hair. Well, in 20 years I'm older, 50-ish. That's close enough. More than likely my hair will be gray. Okay, because the older you get, the more likely it turns gray. So that's like a duh kind of comment. If we look at our elements, 90% of our metals are gray. So that's, who cares? Okay, predicting the mass. So this is saying you in 20 years look at me and you're like, in 20 years you're going to weigh this. That's kind of cool. I mean, be able to pick that up. 72.6 versus 72. Okay. Still, you might say, well, as you get older, you're not going to work out as much, you're going to drop, so you're going to increase body fat and all that fun stuff. So the next one, density. Okay? Now it's not weight, it's what is your body fat percentage. Okay? So in 20 years, you can tell me what my body fat percentage is going to be. You're predicting right now. That's starting to get kind of cool. Like, okay, that's pretty legitimate. Melting point, everybody has a weak spot. Okay? Very high. I think we can make the argument that 937 is very high. He doesn't have to quantify everything. Okay? In 20 years, I know how it's going to interact. So in 20 years from now, I know you're going to have 2 kids. Okay? Arguably off of averages, you might be able to pull that one. Next one, the density of the oxide. 20 years from now, not only am I going to know your density, but if I take the density of your kids and include that with it. That's a pretty impressive guess. 4.7, 4.7. Okay, notice there's an extra 0 there because there's more sig figs when we actually know what it is. Okay, the next one, again, how it reacts with something else, and again, melting points. Okay, so this is pretty phenomenal. 20 years out from now, someone could sit down and say, your body fat is going to be this. If I average in your body fat with your wife, it's going to be this. Or your potential partner, it's going to be this. Okay? If someone told you that now, you're like, you're full of crap. And then 20 years from now, they're right. You're going to be like, whoa, you were really smart. That's why we celebrate Mendeleev. Right?
Was he alive when they found him? Oh, good.
Noble gases. Periodic law. Oh, actually, I want to go back a little bit here. So we celebrate him for this awesome prediction. Okay? One of the other things that's lesser known is he made tons of other predictions that were horribly wrong. Okay? But because he made some that were spot on, we're like, okay, you should be famous for that. And we tend to ignore the failures in his system. Okay?
Why did he change the name of it?
Well, so he didn't change the name of it. It comes from the root. Eka means similar. So in his periodic table here, you notice we got these ekas. Okay? And if we find the silicon one, okay, this one is eka silicon, meaning it is similar to the element silicon. He didn't know what it is, so we can't name it because he hasn't found it. Okay? But according to the organization of his table, he said there's a hole there, and you all as scientists have done a crap job finding the elements. There's an element that belongs there. That element, because I don't know what it is, I'm going to call eka silicon because it's similar to silicon. Why do you pick silicon and not some of the other ones? Silicon is a more commonly found element. Okay. So the eka is just similar to, it's a placeholder name. Okay. Once it was discovered, whoops, jumped too far, then the discoverer got to name it. Where do you think the discoverer existed? Was German. Okay. Keep skipping over it. If we, Mendeleev said organized by atomic mass. That was his theory. As we move further along, Okay? Moseley goes through and says nuclear charge makes sense. Why did Moseley say nuclear charge and not atomic mass? Or potentially the flip, why did Mendeleev not jump directly to nuclear charge? When was nuclear charge discovered? Early 1900s. When are Mendeleev's predictions? 1860. We have no concept of nuclear charge. Right? So there isn't a way for him to go through and organize according to nuclear charge because he doesn't know that there is a nuclear charge. Right? So all he does is organize by mass. Right? Moseley comes through and says there's actually some exceptions to that. So if we look at the periodic table, actually we can, that's kind of small. Right? I'll circle it on this. If we look according to atomic mass, okay, I think the first exception, so we go 54.9, 55.8, bigger, right? Yes, bigger, good. 58.93, bigger. 58.69, smaller. 63.55, bigger. Okay, so we encounter an exception, and if we scanned through this appropriately in my other class, where did I just say that was? There, manganese? Nope, cobalt. Cobalt? Yeah. Cobalt is our first exception. So if we organize by atomic mass, we would place cobalt in the wrong spot. Right? We might say, well, that's not a big deal, but then when we go through and look at the reactivity within a family, we find that cobalt reacts more like rhodium, and iron reacts more like ruthenium. Okay? That's a hard discovery because those are relatively low abundant materials. Once we get enough of an abundance of those, then we can start to see that, oops, that's a mismatch. That's what Moseley was able to go through and do, is say, hey, there's a mismatch here. If we organize by nuclear charge, that mismatch disappears. Okay, so there's a few spots in the periodic table where Mendeleev's trend by atomic mass doesn't work. Okay? That's why we move to the periodic law, which is now by atomic number, so the number of protons. Okay? That's how we get our final periodic table-ish. The last kind of big adjustment comes in the second half of chapter 4, which we haven't talked about. Hopefully we'll get through today, okay, which is kind of the hard part. All right. You all did the quiz. Estimate how long did it take you? How long did you get? What? 10 minutes? 5 minutes? Okay. Just kind of philosophically, why would I have picked all of these n?
Because they're all the same, sort of.
They're all the same, so it's very easy to get those elements confused. Okay? So on an exam, you could fully expect to see what is the name for the symbol N, and your answer choices would be nickel, nitrogen. I might even throw sodium on there. What are some other N ones? Some other N things. Neon, there we go. Right? So we can't go just based off of the first letter in the name because there's lots of repeats. You actually have to memorize those. So spend the time and get those memorized. Right? You also see some other ones like silver's tossed on here. And our symbol for silver was, or is, Ag. Not S, because S would be sulfur. And not Si, because silicon. Okay? So depending on which one you're looking at, you may see some conflicts. That's why those ones in particular get tested on, to actually prove, were you just making things up and going based off of whatever the name said, or do you actually learn those names? Okay? So be aware of that. This one I fully expect to see a bunch of different answers for, but let's change it. What is Mike's opinion? Mike would be me, by the way. Failure. Hey, you guys did a good job. The other class didn't say failure. That's mine. Failure is the most important thing. Okay. The groups and periods were good. Okay. Again, just memorization. Common names. She added something, by the way, on the pnictogens. I just put it on there because I thought it was a cool word to say. She added the origin of it with the choking or suffocating, okay, which I thought was kind of cool. I didn't know that, so that was neat. Okay. Did you guys do this slide all the way through?
Yes.
Okay. So we got a mix there. I heard a I don't think so, and then lots of confident yeses. Okay.
It's hard for everybody to see everything.
This is one where she was off.
Where things shifted a little bit?
Yeah.
Okay. So, what can we predict about francium? Oh, we could ask that question. Ignore the top question. Okay. What is a reasonable density for potassium given this information? Number one, there's a ton of information on here. What should you do? Just look at the density. So you should ignore virtually everything else. Okay. Potassium. What do I know about potassium?
K.
K is its symbol. Where is K with respect to all the elements that are listed? In the giant gray bar. Okay. Yes, that's a bit of a hint, unintentional. You wouldn't necessarily see that on an exam. So if I look at the densities, what happens as I go from lithium to sodium? Increases by how much? 0.4-ish. Okay. As I go from rubidium to cesium, again down the column, what happens? It again increases. So what would I expect to happen to the density as I go from sodium to potassium? It should increase. Okay. How much should it increase? Well, this is why having the full trend can help out. It starts going up by 0.545-ish, and then it starts to go to 0.3. So maybe it only goes up by 0.4. Okay. So a decent approximation might be to call this 1.4. Problem with that is that now gets really close to that one. So a decent guess might be to split the difference. About 1.2-ish. Right? That's what the data shows. So in looking at the question, what does your answer become? B, 1.23. Right? Using the information at hand, that's what we've got. Right? This isn't impossible to tell because I can make a solid prediction based on the data. Yeah? Right. If we remove some stuff, what does that stupid little footnote say?
It was less than that.
Right. Meaning, if we actually remove the gray bar, what is the density for potassium? 0.86. Does that match the general trend? No. What is the answer for the question at the bottom?
Still 1 point.
It is still 1.23. Okay, and this tends to blow people's minds, but it's not 1 point. I don't care. Given the data, the answer is 1.23. Okay? That is what our data leads us to. We have to follow the data. Right? And that is a very challenging concept for students and teachers to deal with. Okay? Particularly if you move into the lab. If you're told to solve for the mass of boron, and you run the experiment and you find that the mass of boron is 15. Okay? Are you right? Boron begins with B. No, the mass of boron according to our periodic table is 10.8. You found it to be 15. So you are definitely wrong. Did your data lead you to 15? Yes. Your experiment is fine. What you would now have to do is draw conclusions about why it didn't get there. And depending on your instructor, some instructors say, well, it was supposed to be 10.8. You screwed up the experiment. You lose points. Some instructors say, you followed the experimental procedure. Yes, you made mistakes, but you've acknowledged those mistakes. You've learned from that. You get full points. Okay? There's two different philosophies in the field. And believe me, you will find both of those kinds of teachers. I'm the one, what does the data tell you? I don't care if it's wrong. What does the data tell you? Okay? So when you see exam questions, look to the data that's given and answer the question based on the data that's given. Okay? So, predicting chemical properties. So I heard that she skipped, which makes me a little nervous. Did you see this slide? No. Okay, well, let's look at it. We took out our columns as families. Okay? If I was to interact with your dad, because I'm male, so of course I'm going to make it male-oriented. Or here, let's flip it. If I was to talk to your mom, I was about to say wife, that didn't work. Your mom, okay, I would get an understanding of how you might act as a person. Why?
Because they'll tell you the truth.
You learn from our parents.
You learn your attitudes from your parents. So if I interact with your mom, I've picked up some information. I can get an approximation of how you might act. Okay? Be it male or female. Okay? Because you're in the same family. But if I talk to your mom to try and figure out how I'm going to interact with the world, that doesn't make any sense because I'm not part of that family. Right? So our periodic table is organized according to these columns and rows, and it turns out that the column has to do with how all of those elements interact with the rest of the world. They're in the same family. Right? So if I want to see how lithium, or a metal, right, reacts with oxygen, I could look at a family and pick a single element, lithium. I'm going to react it with oxygen, and I find out that when it reacts with oxygen, it takes 2 lithiums and 1 oxygen. If I now go through and look to see how potassium reacts with oxygen, which is a different element, but it's in the same column, what do I find out? It reacts the exact same. Okay? So the families give you some information about that predictive ability. Okay? And that is pretty cool. That's one of the reasons why the periodic table organization is exceptionally powerful. We have that information at our fingertips. We have to interpret it and realize that information is there, and that's the hard part. Okay? We're not going to do the activity because I kind of want to move into the other stuff. Okay? But if we were to come up with a possible exam question, of course I didn't write one on here. So let's look at another example. Let's pick, okay, I want aluminum. I want to know the formula of aluminum. So how many aluminums react with oxygen? Okay. The information given, so my given information is going to tell me that I know when zinc reacts with oxygen, there's 2 oxygens. I know that when gallium reacts with oxygen, oh, I had to pick one that I'm not good at the math on. Yeah, just trust me. And that when silicon reacts with oxygen, I'm going to make some changes. Okay. What is the formula for the aluminum oxide? Okay, so if we looked at answer choices, your answer choices are going to be, hello. You're not even going to laugh? Okay. You can at least boo. Give me something. Okay. Connect, thank you. And then we just did 4, but theoretically we'd have 5 answers. Which of those answers is correct? Okay, why is the second one correct? Okay. We know within a family they react the same. So I've given you a bunch of information. If you look at those formulas, all of those formulas show up as answer choices. Okay. So we have to decide which of those best represents aluminum. Well, zinc is close by, right, but not in the same family. So the zinc formula doesn't make sense. Silicon is immediately next to it. Not in the same family. Gallium's in the same family. My formula is going to match gallium. Okay. We now have a multiple choice question. That's how we would work our way through it. We have to acknowledge that our families react the same. Make sense? Okay. And so we're now kind of walking into that area of maybe it was talked about, maybe not. I heard she didn't talk about this. No. Okay. So periodic trends. Chapter 5 is all about trends in the periodic table. So what do you see as trends? So we talked about families. Right? turns out there's tons of trends in the periodic table. We just have to know where to find them, okay, and what thing we're looking at. So one of the trends that we'll look at is atomic radius. Okay? So atomic radius is the size of the atom. Right? If I asked you to describe my size, what would you use to describe that? That's a dangerous question, but let's go with it. What's that? Height. Would anybody else choose something else? Weight. Right? Those are our two standard measurements for size. Right? With a human, because the weight is relatively evenly distributed throughout my height, it's not a big deal. We could use either one and get a ballpark estimate of the size. Atoms, however, the weight isn't evenly distributed. Where is the weight for an atom?
Nucleus.
In the nucleus. If I made the superdome the atom, where's the nucleus? It was a marble inside. Does the marble contribute to the size? Okay, for instance, if I threw that superdome atom at you, are you concerned about the marble hitting you first? No. You're concerned about the rest of it. So the nucleus is not important when we're talking about size. Okay? What was in the nucleus? Protons and neutrons. So what am I concerned about then when I'm talking about size? The electrons. Okay? What would you expect to happen to the atom if I added more electrons? It gets bigger, right? That kind of makes sense. More stuff, it gets bigger. Okay? So when we're looking at our size, we're talking about electrons, so let's address those trends. When we go down a column, so let's pick hydrogen, and I move to lithium. And in this, we're assuming neutral charge. How many electrons would a hydrogen atom have? Rhymes with fun. One. Good call. Right? Because it has one proton, one electron to balance out. It has one electron. I move to lithium. It has 3 electrons. Which one should be bigger? Lithium. Is it true? You all read it, theoretically. Yeah. When we move down a column, the atom gets bigger. Right? So francium is significantly larger than hydrogen because it has significantly more electrons. Okay? And that tends to be the general rule that we sit with. So let's make that our rule. Okay? So rule, for those being like, I need to write this because he's saying rule, that doesn't mean it's correct. Rule, more electrons, I already started, more bigger. I couldn't think to fix it. Right? So let's move left to right now. Okay. Hydrogen and helium, those are tiny. So let's pick something a little bit bigger. Let's look at sodium. Okay. Na, 11 electrons, going to argon with how many electrons? 18. Does it have more electrons? Yes. So what would you expect to happen? It gets bigger. Okay. So down the column, great. We were fantastic. Left to right, what happens? It gets smaller. Remember that rule that we just came up with? Said more electrons, more bigger. Is that rule true? No. Okay. Well, as we move left to right, what else is changing? Charge of what? Don't bring that in. What else changes as we go from sodium to argon? The number of protons. So if there's more positive charge in the nucleus, what should it do to the electrons?
Bring them in closer.
It should bring them in closer. It's a larger positive. It's a larger north end of a magnet. So the south end of the magnet should be attracted closer. Okay, so our rule is, and again, you might not want to write this. Our rule is more protons, and we might as well just commit, less bigger. Okay? Because that explains left to right. Argon has more protons, so it is less big than sodium. Okay? Notice in these examples, I'm not comparing sodium to krypton. Why not?
Not the same.
Not same row and not same column. Too many variables are changing at once. That becomes a little bit more difficult to interpret. Okay? Let's go back to our initial example. Hydrogen to lithium. Our rule is now more protons, less big. What changes as we go from hydrogen to lithium?
Protons.
There's more protons. So lithium should be
More bigger.
less bigger. But that's not true. Okay? So we're missing something. This trend doesn't make sense based on what we understand about the structure of the atom so far. Okay? These trends are absolutely valid. Okay? You are required to answer those, okay, or know those trends. The next part of it, you may be asked as more of an extra credit question. Why is that happening? We just came up with two explanations that are very common for students to use. The instant you use that rule, though, it invalidates the other trend. So our rules are missing a piece of information. Okay? There has to be an and something else. That and something else has to do with where the electrons are going. Well, where are they going? Somewhere around the nucleus. Have we established where around the nucleus in lecture yet? No. That's why our trend doesn't make sense. We haven't addressed where our electrons go. Okay? Our protons we just jammed into the nucleus and we said we were done. The electrons we just assumed were on the outside. That assumption is invalid. Okay? To understand something about where our electrons go takes us back to chapter 4, where now we have to talk about where the electrons exist. Okay, before we get there, some pretty pictures. Lithium to cesium, what happens to it? It gets bigger. Lithium to fluorine, it gets smaller. Okay, so we could look at those pretty pictures to see that trend. Okay, you may also see something like this. In fact, you should see something like this in your the book, textbook. Okay? And they're showing these arrows with atomic radius and metallic character. The metallic character we've already talked about. The more metallic, where are you? The left-hand side of the table. So if we look at these arrows, metallic character decreases as we go from left to right. Okay? That staircase runs not nicely on that one. So let's look at the big periodic table. Okay? So as we're further left, the more metallic we are. The staircase isn't a perfect vertical line. It's not just left and right. It's also up and down. Okay? Bismuth is what? Metallic. Okay? Antimony, arsenic. Now we're transitioning into that nonmetal. So as we go up, our metallic character decreases as well. Okay? And it's all centered around that diagonal. We've already established that. Okay? But now it's drawn on this. The radius is now also drawn on this. Those of you saying, I can memorize that trend without a problem. That's cool. By all means, go ahead and do so. I'm going to tell you that's a bad idea. Instead, what you should do is memorize it for roughly 5 minutes. And I don't mean 5 minutes at the end of class today. I mean the 5 minutes before you start the exam. Or as you start the exam. Because the very second page on the exam is, because you all looked at the practice exam, right? Is a periodic table. What should you immediately do? Draw the trend on the periodic table. It is now memorized. You continue through the test. You see something about trends. You flip to that page where you already wrote the answer down. You now have to interpret it. There's no like, oh, what was that trend? Oh, it was this. My memory's rock solid. I'm fine. Take a test, roughly about maybe question 15. Your brain's going to go to goo. You're not going to remember the trend. Okay? Write it down early. You don't have to think about it anymore. Okay, so chapter 4. And this also makes me nervous because it sounded like she started to talk about some of this. No? Okay, then maybe we're okay. Okay. There's lots of stuff on the wave nature of light, okay, in chapter 4. Ultimately, really all I want you to do is recognize that light is a wave. As a wave, it is composed of two primary things, the frequency and the wavelength. Okay. The wavelength is the distance between two peaks. So if we look at this top one, the distance between those two peaks is now the wavelength. Okay? Wavelength is a really long word. I don't want to write it out every time. So what do? We abbreviate it. So we could come up with W. Did we not come up with W? I don't know why we didn't use W, but we decided W was a bad one to use. What's that? We could do L for length. No. The L isn't quite right because you're looking at the wrong language. We use the Greek L, lambda. Lambda represents our wavelength. Okay? Why? Because it looks cool. Okay? Half-Life fans? Sorry.
Wow.
Oh, wow on that. Jeez. Okay? Frequency, okay, has to do with how many times it repeats within a given distance. Okay? So if we compare the red line to the blue line, the red line barely repeats in that one distance. What happens with the blue line in that same distance? It repeats a bunch more times. So the repeating is your frequency. How many times does it repeat within a defined distance? That is now the frequency. Because we already went into the Greek alphabet for lambda, guess what we're going to do for our symbol for frequency? We're doing more Greek. You'll typically see people call this V. It is not V, because V is velocity, already used by physics, so we can't touch it. Okay, so instead we use frequency. Okay, or sorry, our symbol, I don't know what the Greek name of that one is actually. Anybody know Greek? It's right there. So that's the problem. The symbol looks an awful lot like V. It's not a V. Okay. If we accent it a little bit more, okay, honestly I don't know what the Greek name for that is, but it's almost like an italic V. Okay, that is our frequency. Nu? No, lambda's this one. I think that one might be nu. Well, I don't know. I don't speak Greek. Okay, so we've got a formula, which means what could you be expected to do? Memorize the formula, because what would you then need to do? Solve. Do a bunch of calculations. How many of you want to do a bunch of calculations?
Never.
Cool. We aren't going to do it in this class. Okay. If you move into 151, yes, you will use it a lot. Okay. But in this class, we aren't concerned about it. What we're more concerned about is the relationship between the energy and those symbols. Okay. So if the frequency increases, if this V value gets bigger, what happens to the energy? Okay. H, does anybody know what H is? Call it 1. If V gets bigger, what happens to E? It increases. It's a direct relationship. So the higher the frequency, or the larger the frequency, the larger the energy. Okay. If we go through to incorporate how lambda fits into this, okay, again, not a big deal. It's hc over lambda. What happens when we increase the wavelength? What happens to the energy? Okay, it decreases. This value gets bigger. This number in blue gets smaller. Okay, so we see an inverse relationship between wavelength and energy. We see a direct relationship between frequency and energy. Well, that's all I want out of it. Okay? When we look at light, we typically only think about it as the visible spectrum. Turns out the visible spectrum is a very tiny portion of the electromagnetic spectrum. Okay, why do we not refer to light as the electromagnetic spectrum?
Because it's long.
It's a really big word. You've got electro and magnetic. Okay? Magnets, oh, those are cool. I play with those all the time. Electricity, I stick a fork in the outlet, that hurts. If we call light the electromagnetic spectrum, what happens? It scares people. Okay? And for those of you thinking that's not that big a deal, has anybody had an MRI? Yeah. Stands for magnetic resonance imaging. Those are some big, scary words. It's actually nuclear magnetic resonance imaging. And now you're like, nuclear? Holy crap. There's nuclear bombs that like kill cities. And you're putting me in an instrument that does nuclear stuff? Yes. Not a big deal. Okay? It's that word association that scares people. So when they took the technology of NMR, nuclear magnetic resonance, and then made it where they put people in it, they found that people wouldn't go into the instrument. You drop the N, and everyone's like, okay, it's magnets. I play with magnets and resonance. I don't even know what resonance is. Who cares? Okay? And they're all okay with it. A subtle word change allows for that technology to transfer. Okay? So it is a really big deal. That's why we just refer to it as the visible light spectrum. Why else do we refer to it as visible light?
Because we can see it.
We can see it. Okay, there was a hand?
Yeah, you were right. It's new. NU.
New? Cool. Oh, it's NU too?
NU.
Okay, that's exactly how I was going to spell it.
So I have a question.
That's a lie. I was going to spell it GNU.
When you go for the MRI, sometimes they give you IV,
Mhm.
and they give you something so they can see it in your blood,
Yep,
and that's because of the magnets or because of the chemicals?
the magnets. So what they're using is they're detecting the nuclei. That's why it's nuclear magnetic resonance. They're detecting the nuclei of a particular species. So they inject you with something that is susceptible to the magnetic fields so that they can see it.
That's why you get all warm when you're trying to pee.
Well, you get all warm because you're going to pee because what they give you is iodine. And iodine, for whatever reason, makes you feel like you're going to pee. Yeah. Which is a really weird experience, by the way. If you've ever had that injected, it's like, what the? Yeah. Yeah. Any case. So, some other kind of questions can come out of this is which has higher energy? Red, green, blue, or yellow? Blue. Okay. How would we know that? Okay. So you know that. That's awesome. I like it. You know that because you looked at the picture. What is your exam going to look like? So I love your jump. That was awesome. But that doesn't work always.
Now I'm going to remember it.
Okay? So ultimately, you're going to have to memorize the pattern behind it. Okay? It took me a while to deal with it, okay? But I ended up thinking about the rest of the light spectrum. When we go past purple, okay? What's another name for purple? Violet. What if we're really, really, really violet?
Ultraviolet.
We would be ultraviolet. Okay? What if we go past red?
Infrared.
We might go ultra red because, might as well stick with it. Unfortunately, we go infrared. Okay, but at least part of that is there. When you walk out into the sun, what are you concerned about? Ultraviolet. And that's why, what do we put on ourselves? Sunscreen or sunblock to absorb the ultraviolet light. Why are we trying to absorb the ultraviolet light?
So we don't get skin cancer and that.
Why are we getting skin cancer? The ultraviolet light has higher energy. That higher energy is what causes damage to our cells. That's why we put on sunblock. Okay? The sunblock absorbs that energy instead of our skin. Okay? So when we go out into the sun, we're concerned about ultraviolet because that is dangerous. Which is closer to the high energy ultraviolet? Violet or red? Violet. Okay? That can help you set up the spectrum. Purple is your highest energy. Red is your lowest energy. Okay? What colors are in the visible spectrum?
Cat in the Hat taught me the rainbow song.
Okay, what's your rainbow song?
Ready?
All right, so we can go for it, yeah.
Red, orange, yellow, then green, followed by blue. Indigo and violet, that's the rainbow song for you.
Cool. I had not heard that one, but it actually worked out for us. We started with red, orange, yellow, green, blue, indigo, and violet. And some people already started mumbling it out. The famous scientist that discovered the rainbow was known as Roy G. Biv. Totally false. That's just the abbreviations we used. Okay? And for whatever reason, people seem to remember Roy G. Biv. Okay? Notice that's in the opposite line as how it's set up here. That's arbitrary. All you need to do is remember that red is low energy, violet is high energy. Okay? Again, this could be just one of those memorization things. You purge it onto the exam, you could answer a question about it. Make sense? Okay. So why are we talking about light? Okay. We're talking about light because somebody, when they discovered electric current, said, I wonder what happens when we put electric current through things. You're like, they never wondered that. How many of you have stuck a 9-volt battery to your tongue? Yes, we wonder that. What happens when we put electric current through it? Because when we put it through people, they tend to respond and go, ow. Okay? What happens when we put it to elements? Okay? Depending on the phase of the element, we see different responses. Okay? So one of the things that we could do is we had a vacuum, and in that vacuum, what would be in it? A vacuum.
Nothing.
Nothing. So what should happen when I put electric current to it? Nothing. Okay? Instead, what did I see? Ooh, there was some color because there was trace elements present. So then we said, well, okay, what if I put in a pure element into that tube? Okay? So I'm going to put in just hydrogen. Now when I pump the electric current through, that electric current is going to hit hydrogen atoms and only hydrogen atoms. What does it do? Well, it turns out it fires out this kind of purple color. Okay? Visible light that we see here spits out which color? Where's white on this spectrum? White is all colors. So how do we know that all of those colors are in white light? Because we could put it through a prism. So somebody said, well, if white light is all of these colors, perhaps the purple light that I'm seeing coming from this hydrogen lamp is actually something more than purple. So I'm going to put a prism in front of it, and when I put that prism in front of it, I do indeed see a division. And in that division, what I end up seeing is 3 lines. Black space, and then a violet band, a blue-green band, and a red band. Okay? So the purple light that we're seeing for hydrogen in particular is composed of those 3 things, okay, or those 3 energies. Okay? Well, where did those energies come from? Okay, well, what did we do to get those lights? You excited it. You put a bunch of electric current into it, and you said, let's see what happens. Well, this is what happened. Okay? We don't see only purple light, or a big smattering of purple light. Okay? We don't see something like that where that's all colored in. We see these distinct bands. Again, what did we put in? Electric current. What is electric current? Electrons. So these colors are likely due to the electrons. The electrons where? In a hydrogen atom. Interesting feature of this. So really what we're saying is we put a bunch of energy in, and the electrons inside our atom decide to dance. And in that dance, when they relax back down, okay, so they absorb that energy, and they say, well, I'm done dancing, they relax back down, but they have to get rid of that energy somehow. That energy they get rid of is visible light. The extra interesting thing here is that it's not a spectrum of visible light. It is a single light. It is only this violet color, only this blue-green color, and only that red color. Nothing else. Okay? Which means when they get up to dance and they relax, they are only doing that in very distinct patterns. Okay? If I told you all to get up and dance now, we're going to have varying amounts of dancing. Okay? Admittedly, probably none, depending on how many is actually going to agree with me on this. Okay? Some people may go, oh, this is totally cool. I'm going to get up and dance because I like to dance. Okay? You'll probably be super active. There'll probably be somebody going, dance? I don't want to fucking dance. This is crap. I'm not doing that. I'm going to watch somebody else dance. Okay? And then you'll get varying people in between. You'll get an entire spectrum of different people dancing. For the atom, that's not true. Okay? You get people dancing with tons of energy, some with a little bit of energy, and some with no energy. We don't get anything in between. Okay? We only get these exact points. That's weird, because that means the electrons can only exist in exact points. So our theory that the electrons are just somewhere outside the nucleus is now debunked. The electrons are existing in particular locations outside the nucleus. Okay? Niels Bohr is the one that went through and looked at this and said, you know what? Here are the exact locations. These locations are how the electrons are moving around a nucleus. I know Earth moves around the sun. And when I describe Earth's motion around the sun, I would define that as the orbit. So what did he use for the terms?
Orbit.
Orbits. Right? That's what those are representing. That's what we're trying to get to. Right? So he defined these orbits. So if we looked at a hydrogen atom, that hydrogen atom has only one electron. Where should that one electron go in these orbits? Why the first one? Are electrons stable? Walking through the air, zap! Oh, ow. Okay. Do electrons just exist on their own? No, which means they're not stable. They need to be balanced out by something, by protons. So where should the electron go? As close as possible to the proton, because that cancels the charge. Right? So I want to get it as close as possible. Okay, so there's my hydrogen atom just chilling along, happy as can be. And now I pump 20,000 volts into it. What does that electron do? Okay? Think about it this way. You're all sitting down. Under one of your seats, I put a little electric buzzer. Okay? So when I push this button, we'll see what happens when that electric buzzer hits you. We ready? I didn't actually do that. What would that one person have done? Jumped. What is that electron going to do when I give it 20,000 volts? It's going to jump. Where can it jump? It can only jump to another orbit. Okay, so let's say our electron, 20,000 volts, jumps up here. Okay, so I've given it this cattle prod of energy. We'll call that cattle prod because it's nice and scientific. And it jumps up to this higher energy. Okay, that person, if I said, now people should dance, that one person is probably going to jump up right when I cattle prodded them. I'm going to dance to stop cattle prodding me. There's our electron. It's now jumped up. Okay. Eventually what happens? I put the cattle prod away, and what do? You probably sit back down. Okay. We're at a higher energy state, though. Okay. If I drop back down, I'm dropping in energy. I cannot destroy energy.
So could you say the closer to the nucleus the electron is, the weaker the charge it has?
Yes. Closer to the nucleus, the weaker the charge. What happens to that excess energy? It has to be removed somehow. The way it's removed is through an emission of a piece of energy that happens to be related to h, which is Planck's constant, and our frequency, or hc over lambda. Our frequency and our lambda were representations for energy of light. Isn't quite good enough. Wavelength's already specified in there.
Electromagnetic spectrum.
the electromagnetic spectrum. Yes, I know. If the energy of that electromagnetic spectrum is perfect, what do we see? Visible light. And it turns out that when we inject 20,000 volts into our hydrogen atom, what we are seeing is the electron relaxing back down. Because we put the cattle prod away, it says, okay, relax back down. In the process of relaxing back down, it emits that energy. Okay? Well, that energy would be specific to what? The color of the light. Well, when we looked at our hydrogen, how many colors of light did we have? 3. Well, I just described 1. Where are the other 3? Okay. The electron doesn't have to jump to just orbit 2. It could have jumped to orbit 3. What happens if I jump to orbit 3? I'm going to dance faster. Well, what happens when it relaxes? It's going to release more energy. Okay? So I've got 2 lines shown here. Okay? Our hydrogen had 3 lines. Okay? We had purple, green, and red. Okay? That's 33% chance you're right. Let's be nicer. Okay? And let's remove one of them, get rid of the green. We've got 2 lines. We'll call them line 1 and line 2. Which one's the purple line? 2, because it's a larger jump. Okay? Which one's the red line? 1, because it's a smaller energy jump. Okay? Does it have to emit visible light? Okay? Turns out there's a lot more orbitals than just 3, or orbits than 3. Okay? We'll stick with just 7 for the moment. So if we continue to go out, okay, we could go all the way up to the 7th and look at that jump. If 2 was purple, what is the 7 one going to be? Something we can't see. That is now outside the visible spectrum. We aren't going to be able to see that. It's still happening, we just can't see it. Okay? Because Niels Bohr looked at those orbits and said, or used orbits to explain this observation, he gets credit for determining where our electrons exist. Okay? One of the big terms that come out of this is our electron energy is quantized. When we put that 20,000 volts in, the electron can only exist at those orbits. Like, that's not a big deal. What about this space where that purple is? Is that an orbit? No, the electron can't exist there. It can only exist at the orbits. Okay, which means very defined energy levels. Okay, and you might again say, well, I've never experienced things like that. Okay, how did you get up to this floor? Stairs. How many of you took a step and a half? Why did you not take a step and a half? There's no step there at a step and a half. You took potentially step 1. You might have even done step 2. How many of you took step 3? Right, that's a bit harder. Why is that harder for you?
Requires more energy.
You need more energy and longer leg stride. Okay, you probably can't pull that one off. You took steps. Did anybody take another way up to this room? Probably didn't, but we could have used an elevator. So we get on the elevator and what happens? It's a smooth transition. There aren't steps. You can exist at every level in the elevator. The elevator is now a continuous process. Okay? Our atomic or our electron existence is not continuous. It's discrete. Okay? We have discrete energies. This is our quantized system. Okay? We could have also used a ramp instead of an elevator. Okay? That would have worked equally well. Okay? And I really hate to do this, but I'm going to have to pause the video. Jumping up is an absorption of energy. If it's absorbing energy, we can't see it. If anything, it would show up as black because there's no light actually coming back to you. Okay, so it's only when it comes back down. So if we go through and look at Bohr's model, they've added a little bit more information to it. This is effectively what we just drew. Okay? Here's our first orbit, second, third, fourth, fifth, sixth, seventh orbit. And it turns out the lines that we're seeing are when the electron jumps from the fifth to the second, the fourth to the second, and the third to the second. Anybody see anything weird about that? You can ask your question and we'll go back to it.
I was just wondering if it's just the drawing or if there's an actual reason why the steps are getting smaller as you go up.
We'll talk about that. There's a reason behind it.
Okay.
Anybody see anything weird or different about this in comparison to the last one? Why are they not jumping to the first? They are. But if we jump to the first, that's more energy, which is outside of our visible light spectrum. Okay, so when our electrons get ejected up, they can drop to any energy lower than it. So from that fifth, I could drop to the fourth. But it turns out that drop in energy is so small that it's now outside of my visible spectrum.
So it has to be a good drop in it.
Okay. So the drop in energy has to exactly match the energy of the visible light spectrum. If it doesn't match, then we don't see it. That doesn't mean it's not happening. It just means we don't see it. Okay? Once we go through the quantum, and by we I mean as a field of people, go through the quantum mechanical processes for how an electron exists, that's how we can go through and predict that what's happening is a jump from the fourth to the second, okay, or the fifth to the second, or the third to the second, and not the first. Okay? That involves, if you didn't catch that, quantum mechanical mathematics, which is ultimately a fancy way of saying stuff well outside the scope of this class. So you don't need to worry about those calculations. 151 gives you the formula, and you have to use the formula to calculate it, but arguably where the formula came from is well outside the scope of that class too. Right? So don't stress per se about it. Right? Really at this point, all I want you to do is recognize that these jumps, the visible light that we're seeing, correspond to orbital jumps. Which orbital jump? That, again, I don't really care. What I would care about is that if I gave you two orbital jumps, you could tell me, based on two color options, what the color was. Okay, which we just walked through. Does that make sense? Yeah?
So when you're jumping back in it and it's light, how long does that light last for? Like, are they just constantly jumping back and forth?
Yes, they are constantly jumping back and forth. So that light would exist until it impacts something that prevents it from passing on. Okay, so it would just kind of radiate outwards. Okay. When we're doing this with the lamps, you're turning on the electric current. When did you turn off the electric current? Well, at this point, I didn't talk about turning off the electric current because we don't. We leave it on. We leave it on until we can make all these observations. As soon as we turn it off, we're now no longer generating excited states, which then means no excited states, no light emission. So it's only with that electric current being pumped into it that we'd see the light. Okay? The thing that's also neat about this, particularly if you've taken like an astronomy class, is that every element has a different line spectrum. Okay, so they're referred to as the atomic fingerprints. So if I looked at through a prism of some unknown species and it produced these colors, I would know that whatever that unknown species was, it was helium. Okay? And we can do this on astronomical scales, meaning I aim a telescope at some star, okay, or some planet, some source of light. I can then separate out through a prism that light to determine what elements were present at that point that I was looking at.
What's the unit in?
We'll talk about that too, not quite yet.
Would elements in the same families have similar atomic fingerprints?
That is a good question that I'm going to cheat at and say no, but the only reason why, anybody notice what I was doing when she asked the question? I looked back and forth at the periodic table and the ones shown here. Lithium and sodium are in the same family. Is the atomic line spectrum the same?
No.
No. Why would it change? Aren't the orbits all the same? What happens as we move from hydrogen to helium? The atomic radius increases because more electrons. What else changes? What contributes to mass? The protons, which means the nucleus changes its strength. I add more electrons in, so it could potentially get bigger, but I'm changing the energy of the nucleus, which means the electrons could get drawn in tighter. So every time I transition from element to element, the orbitals all change their energies. Right? So I can't have a single drawing and say this is all of the orbits for all elements at their exact energies, because it's not true. Every time I transition to a new element, those orbitals will change energy. Not a lot, but enough that the atomic line spectrums are not easy to predict, per se. Let's just say that. Okay? There was a question about NM. NM is nanometers. It's a measure of length. Okay? So when we look at red light, it has a wavelength of 700 nanometers, right? Which is a very, 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 very tiny number. Okay? Because we aren't doing any calculations, I've left that kind of discussion off until Unit 2. When we start to bring in calculations, we'll get back to that nanometer thing. Okay? So, to a first approximation, all the orbits are roughly the same. So we can create a diagram that represents all atoms. We can't quantify anything off of it. Okay? The quantification is what you were getting at. Can I predict based on different elements? And we said the orbits change their energies slightly, so I can't predict numerical values. But I do know that the lowest orbit is 1, the next lowest orbit is 2, the next is 3, 4, 5, so on. Okay? So I can create a picture that represents the electron homes. Okay? So, officially, where I'm writing nucleus is in a horrible, horrible space. Okay? Because that's saying that this first energy level is very close to the nucleus. It is close, but it ain't that close. Okay? More appropriately, the nucleus should probably be drawn somewhere on the first floor. Okay? My screen isn't big enough. Okay? So this is our first energy level. What do we want to call our first energy level? Okay, we could call it orbit 1. I'm lazy. 1. Okay. What happens is my electron gets further and further and further from the nucleus. Okay, it gets higher in energy until it escapes. So there is a cap on our energy levels. That cap is what is referred to as the vacuum. 2 C's? And then 2 U's?
No.
1 C, 2 U's. Let's just do that. That's our vacuum. Okay? Which, believe it or not, is going to get back to your question earlier about, didn't it look like they shrunk? Yeah. This first one is very close to the nucleus. Okay, the next one would go where?
A little ways away.
A little bit further away. Okay? Should it be halfway in between?
Maybe not quite.
Probably not. Because as I continue to add more, it's going to become harder to put all those things in. Okay? Or more orbits, it becomes harder to put those things in. It turns out that this first shell shields the nucleus. So that when I put in the next set of electrons, they have to get further away than this one is from the nucleus. So the stacking behind these what are you talking about? Nothing happened. Where does the third energy go? Okay. Above that. Well, where above that? If I go the same distance, there's the third. Okay. Well, how many orbits do I have? 7. How do you know it's 7? Okay. I told you. Where else? How many rows are there on our periodic table? 7. Don't count the bottom ones. We'll discuss that later. Those are actually supposed to be embedded. There are 7 rows. You mean the periodic table tells me how many orbitals there are? Yes. Awesome. Right? If I try to put equal distance, eventually where's the seventh one going to go then? Outside the atom, in the vacuum. That clearly doesn't happen because I have elements in the seventh row. So the electrons are going to have to get closer and closer, or smaller and smaller gaps between them, because my cap is the vacuum. Okay? So the gap starts to shrink as I go up in energy. See, did I do this nicely? That's not the button I wanted. I wanted that button. Yeah, cool. There we go. So we see them get closer and closer, which was exactly your question. Why did they not maintain the same distance? We have a cap in energy. That's our vacuum. There are 7 of these. Okay? Let's place the first electron. Where should the first electron go? It should go to the first orbit. Why should it go to the first orbit? That's how they fill. Why do they fill that way? Why do I want it closer to the nucleus? To cancel the charge as much as possible. Where's the next electron go? Next to it. What happens when I get an electron or a proton near a proton? They repel. So how do I build a nucleus? I need neutrons. If I put another electron in that same orbit, what are those electrons going to do? Repel. So our first theory probably is not putting it there. Where should the next electron go? It should go to the second orbit. You should very quickly see there's a massive issue with this. If there's only 7 orbits, how many electrons can I have? 7. Does that explain 118? Nope. So there's something wrong with the theory. It turns out as we move up in energy, each of those energies split into what we could call as sublevels, or what I prefer to call as orbital types. So we start at the first energy level with 1 orbital type. When I move up to the second energy level, I now have 2 types. Third, 3, 4th, 5th, 6th, 7th. Okay? I could still go through and do this, and it's still not going to work. Okay? It still doesn't account for everything. Okay? I need to actually start placing 2 electrons into a single orbit. Okay? And the reason I'm allowed to do that for a very silly quantum mechanical, for a very silly explanation, they spin opposite directions. Okay? The quantum mechanical is way worse than that. Every orbit can hold 2 electrons because they're spinning opposite directions. That means they don't interact with each other and they can go in at the same energy level. Okay? And I know apparently none of you are looking at time, but here's our split out. Let's see, did I split it nicely? Not quite. I promise we'll talk about this. As we move up, we increase types. Those types then add an extra thing, orientation. Okay? Give you an idea, sphere, dumbbell. Can you tell I rotate a sphere? No. Could you tell I rotate a dumbbell? Yes. What does that mean? There are different rotations or orientations for the dumbbell. There happen to be 3 of them. As you move further up, you get more orientations, which means more orbitals, more electrons. That explains our final picture. We'll build this on today's Thursday, right?
Yep.
We'll build this on Tuesday, and we'll just see where we go from there.